There is this fascinating psychological trick in the tech world. If you name something tiny or, mini or micro,
People just relax.
exactly. People instinctively lower their guard. It sounds cute. It sounds manageable, safe,
It does. It sounds harmless.
right?
Like a weekend project you'd run on a Raspberry Pi to teach your kids some coding. Tiny implies that, if it breaks, it's no big deal.
Right. And that is exactly the trap we are walking into today. We are doing a deep dive into the tiny web server.
Ah, yes.
On the surface, it's a simple, stripped-down web server, but underneath, it is a masterclass in how digital breaking and entering actually works.
It really is. And to be clear, we aren't just picking this apart for the sake of it. This entire deep dive is based on a legendary text, Hacking the Art of Exploitation by John Erickson.
Oh, that's a classic.
In the cybersecurity world, that book is... It's basically the Bible for understanding not just that software breaks, but why it breaks, down at the binary level.
It's one of those books that doesn't just give you a script to run, right? It actually shows you the C code, the memory structures, the hex dumps. It forces you to look under the hood.
Which is a critical distinction.
Yeah.
We aren't just going to crash a server today. Any script kiddie can do that.
Right, a denial of service attack, flood it, and it tips over.
Exactly. Our mission today is much more sophisticated. We want to understand how you take a crash, a moment of absolute chaos in the system, and turn it into absolute control.
Okay.
We're going to cover stack overflows, writing custom shell code, and my personal favorite part of this whole analysis.
What's that?
Bypassing a firewall by tricking the victim into calling you.
That last part is pure social engineering applied to code. I can't call you, so you call me.
Precisely.
But, okay, before we get to the spycraft, we need to understand the victim. What exactly is this tiny web server?
So TinyWeb is, well, it's exactly what it says on the tin. It's a minimalist web server. Think of the big players, like Apache or Jinx, as these massive industrial factories with security guards and cameras and ID checks.
And tiny web is what? A lemonade stand?
A lemonade stand. Perfect analogy.
Mhm.
It speaks HTTP, the language of the web, but it has a very, very limited vocabulary.
So it's not running complex scripts or databases or anything like that.
No, absolutely not. It handles exactly two types of requests, GETty and head.
So when you type a URL into your browser, you're sending a get add request.
Yep. You're just asking the server, please go into your folder and get me this specific file. TinyWeb looks in its local directory, which is called webroot. If the file is there, it sends it over.
And if it's not there, you get the classic 404 error, file not found.
Simple, functional, and period. For our purposes today, incredibly dangerous.
And the source material has us running this in a Docker image, right?
It does, which is smart.
It's like a sandbox, so when we inevitably blow this thing up, we don't accidentally brick our own machines?
Precisely. It keeps the wreckage contained. But inside that container, the code has a fatal flaw. It's a textbook example of a Stack Overflow vulnerability.
Okay, we hear that term constantly, Stack Overflow. Usually it's just the name of the website developers use to copy-paste code.
Ah, right.
But physically, inside the computer's memory, what is actually overflowing?
To get this, you have to kind of visualize how a program uses memory. It uses this structure. It's called the stack.
The stack, okay.
And honestly, the best way to picture it is literally a stack of dinner plates at a buffet. When a function runs like receive a request from the internet, it puts a new plate on top of the stack.
And that plate holds what? The data for that task?
Exactly. Just the temporary data for that one specific job. That plate is its buffer. And when the function is done,
It takes the plate off.
it takes the plate off and moves on. Now, in TinyWeb, there's a specific function called recline. Its whole job is to listen to the internet and accept the text request you're sending.
Okay, so it's putting a plate on the stack to hold that request.
Right. And the plate has a specific size. But here is the flaw. And it is such a classic C programming mistake.
What is it?
The code doesn't check if the amount of data you're sending actually fits on the plate.
Oh, so if the plate can hold, say, 500 bytes of text and I send 1,000 bytes.
You don't just stop at the edge of the plate.
Yeah.
You keep writing data onto the table, onto the floor, and most importantly, you write over the data that was sitting underneath that plate on the stack.
You're overwriting the memory of the program itself.
Worse, you're spilling your drink on the instruction manual because one of the things stored on the stack right next to our data buffer is something called the return address.
This is the bookmark, right?
That's a great way to put it. When a function finishes, it looks at that bookmark, the return address, to know where to go back to in the main program. It's like I'm going to go get the mail, but when I'm done, I need to come back to the living room.
But if we've overflowed the buffer with junk data,
We've scribbled over the bookmark, we've erased living room, and written gibberish. So when the function tries to return, it reads our garbage data as the address. It tried to jump to a memory location that makes no sense. The CPU gets confused, panics, and the program crashes.
a segmentation fault.
Yeah.
Game over.
Game over.
So that's step one. We've proven we can break it. The source calls this the crash. How do we actually trigger this in practice? Is it complicated?
It's surprisingly crude. You just scream at the server.
You scream at it.
I mean, metaphorically.
Mm-hmm.
TinyWeb expects a request to end with a specific signature, a carriage return, and a new line. That's the digital signal for I'm done talking.
So if you just keep sending data and never send that signal...
The recline function just keeps accepting it. It keeps stuffing it into the buffer, waiting for the end that never comes until it bursts.
Mm-hmm.
The source is just sending about 1,000 bytes of junk, literally just the letter A repeated 1,000 times.
And that's enough to kill it.
Instantly. But here is the pivot point. A dead server is useless to a hacker. It's an annoyance, not an entry point. We need to turn that crash into a hijacking.
And this is where the forensics come in. The source walks us through using GDB, the GNU debugger.
It's exactly like doing an autopsy on the crash.
Huh.
You restart the server, you attach the debugger to the running process, and then you crash it again. But this time you're watching it die in slow motion.
What are we looking for in the wreckage?
We're looking for the offset. Remember, we sent the 1,000 A's. We need to know exactly which A overwrote the return address. Was the 500th A? The 504th A?
Why does that level of precision matter so much?
Because if we know the crash happens precisely at byte 504, we can craft a very specific message. We send 504 bytes of junk to fill the buffer to the brim.
Yeah.
And then the very next 4 bytes we send are the specific memory address that we want the computer to jump to.
I see. So we're replacing the scribbled bookmark not with gibberish, but with a map to our own malicious code.
That's it. We are hijacking the instruction pointer. That is the holy grail. Instead of the program going back to its normal routine, we send it somewhere else. We send it to open the safe.
So we have the keys to the castle. Now we need to decide what to do. This brings us to the bind shell.
Or, as it's known, pwning the server.
Pwning, P-W-N-E-N-ing. It's gamer speak for owning, right? Total domination.
Exactly. We want to inject code that gives us a command prompt on the victim's machine. The first method the source explores is the bind shell.
Okay, how does that work?
Essentially, we inject code that tells the server, stop serving web pages. Instead, open a new port, say port 9999, and just listen for a connection.
So it turns the server into an open door.
A wide open door. If the exploit works, the attacker can use a tool like Netcat to connect to that port, and suddenly you're not a web visitor anymore. You're a user logged into the system.
Now, writing that code, the actual shell code, that sounds incredibly complex.
It would be, but thankfully we have tools. The source uses a plugin for GDB called GDB PETA. It has a brilliant feature where you can just tell it what you want. You run a command, and it spits out the machine code for you.
It's like a vending machine for exploits.
It really streamlines things. But you can't just throw that raw code at the server. You have to package it correctly. And this introduces one of my favorite concepts in all of hacking, the NOP sled.
NOP sled.
It sounds like a winter sport for programmers.
It stands for no operation. In computer code, a NOP is an instruction that tells the CPU to do absolutely nothing for one cycle and just move on.
Why would you ever want the computer to do nothing?
Because memory is slippery. It shifts around. When we inject our shellcode, we don't always know exactly where it will land. If our return address points just 1 byte off, it misses the start of our code and the whole thing crashes.
It's like trying to land a helicopter on a very small pad in the dark.
Exactly. So the NOP sled creates a giant landing pad. We put a huge runway of do-nothing instructions before our malicious code.
Oh, I see.
If we point the return address anywhere inside that sled, the CPU hits it and it just slides down the NOPs, doing nothing, 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 until, bam, it hits our shellcode and executes.
That is brilliant. It turns a precision shot into a shotgun blast. You just have to be close enough. Right. So the final payload is this sandwich. A massive NOP sled, our bind shell code, and then the new return address that points back somewhere onto the sled.
And the source provides a Python script to build this binary sandwich, I assume.
It does, shellcodewriter.py. You have to. You can't type this stuff with a keyboard.
So we send this package, the server chokes, the stack overflows, the instruction pointer gets overwritten with our address, it jumps to the sled, slides down, runs the shellcode, and opens port 9999. We connect with Netcat, And we're in.
We're in. But, and there's always a but in security.
What's catch?
This bind shell technique is a bit, well, it's a bit 1990s. It's easily blocked. We call this the firewall problem.
Right, because most modern networks are not just wide open.
Exactly. Think about a corporate firewall, or even the router in your home. They operate on a principle of default deny for incoming traffic. They're the bouncers at the club.
So random people on the internet can't just connect to some weird port on my laptop.
They can't. So if we use a bind shell, we successfully open the door on the victim's computer. But the firewall is standing in the hallway, ensuring nobody can walk through it.
So the attack fails, not because the code was wrong, but because the network security did its job.
Right. The exploit works, the port opens, but we can't get to it.
So the bind shell is dead on arrival in a secure environment. What's the workaround?
You have to flip the script. Instead of you connecting to the victim, you make the victim connect to you. This is the reverse shell.
And this relies on the fact that firewalls are usually much more lenient about outgoing traffic, right?
Correct. Employees need to browse the web, check email, download updates. If the firewall blocked all outgoing connections, nobody could work. So usually if a call is coming from inside the house, the firewall just waves it through.
So the new strategy is I, the attacker, set up a server on my machine and just wait.
You set up a listener, then you send a different payload to the victim. This shellcode doesn't open a port, it tells the victim machine, call this IP address, the attacker's IP, and connect.
The firewall sees an outgoing request, thinks it's legitimate traffic, and lets it pass.
And once that connection is established, the data flows both ways. You have your shell, you've completely bypassed the perimeter security.
Now, the source material gets very technical here about how this works. It mentions some cryptic bash commands with devtcp and file descriptors. Can we decode that? It looks like algebra gone wrong.
It's actually quite elegant once you see it. In Unix and Linux systems, there's a philosophy. Everything is a file.
Your hard drive is a file, your keyboard is a file.
And your network connections are treated as files. So talking to a network is just like writing to a file. The command redirects standard output, the text that would normally print to your screen, into that TCP connection file.
So the victim computer is sending its screen output to me, the attacker. I can see what the server is saying.
Right. But seeing isn't enough. You need to send commands back. You need to type. That's where the 0 and 1 part comes in.
0 less than a 1. It looks like a typo.
It does. But here's the decoder ring. In Linux, 0 is standard input, your keyboard. 1 is standard output, the screen.
Okay, 0 and 1.
That command, 01, says, make the keyboard input 0 come from the same place as the screen output 1. And since we just pointed the screen output to the network...
You've effectively hotwired the computer so that its keyboard is now the network connection for me.
Exactly. You've rewired the nervous system of the shell. Its eyes, ears, and mouth are all connected to that one socket.
That is terrifyingly clever. It shows that if you can execute code, you can change the fundamental reality of how the OS behaves.
And once you have that reverse shell, you have full user access. You can read secret files, delete data, install new backdoors.
Now, we've gone through this manually calculating offsets, generating shellcode, it seems, labor-intensive, and really prone to human error.
It is. If you miscount by one single byte, the server just crashes and you get nothing. That's why professionals automate everything.
This brings us to ParentTools.
ParentTools is a Python library built specifically for this. It handles all the plumbing. Instead of you manually running things in different windows and hoping you time it right, ParentTools can spin up the process, send the payload, and handle the interaction.
And the source has a script, exploit.py, that does exactly this.
It's a great example of how you move from understanding the theory to weaponizing the vulnerability. It makes the attack reliable and repeatable. You just run the script and pop, you have a shell.
There was one specific gotcha in the source about ParentTools that I found interesting. It mentioned Jupyter notebooks.
Oh yeah, that's a great detail. A lot of people love Jupyter notebooks because they're interactive, but the source warns that if you try to run these scripts inside a notebook, they usually fail.
Why is that?
Because ParentTools tries to take over the standard input and output to interact with the shell. But Jupyter notebooks also capture those inputs and outputs for their own interface.
They fight over who holds the microphone.
Exactly. And the connection usually just hangs or shuts down. So the pro tip is, run it as a proper script from the terminal. Don't let your tools fight you.
So stepping back, we've gone from a harmless, tiny web server to a complete system compromise. We've seen how one tiny slip-up, not checking the size of the dinner plate, let us rewrite memory, inject instructions, and fool an OS into handing us the keys.
It's a pretty sobering journey, from a 404 error to root access.
It makes you wonder. TinyWeb is an educational tool. It's meant to be simple. But is this kind of thing rare in the real world, or are we just picking on a toy?
I wish I could say it was rare, but C and C plus the languages that power most of our critical infrastructure, from operating systems to routers, they manage memory manually if a developer forgets one check.
The vulnerability is there. And as we learned, firewalls won't save you.
No. As we saw with the reverse shell, firewalls are designed to stop people from barging in, not to stop the call coming from inside the house. If the software itself is flawed, the perimeter security is irrelevant.
That's the big takeaway here, isn't it? Security isn't just something you bolt on afterwards. It has to be baked into the code itself.
Exactly. Every time a developer writes a function to receive input without checking the length, they are potentially leaving a door unlocked. It doesn't matter how tiny the application is.
And as we learned today, all it takes is 1,000 bytes of junk data to kick that door wide open.
And a little bit of clever redirection.
And a little NOP sled to slide right into the driver's seat.
Just keep your hands off the production servers, all right?
No promises. But seriously, to our listener, thanks for joining us on this deep dive. It's a reminder to look closely at the tiny things in your code. They might be hiding giant problems.
Until next time. Watch your stack.
See you then.